system. So with that, let me get started and talk about how to maintain calibration models. And specifically what I would like to talk about is how you handle calibration models when you have a lot of calibration models that you need to look into. And I'm talking about tens or hundreds of models. And this is work that was actually done by Helene, a student here at this university quite some time ago, and also a dairy company called Arla, which is a large dairy company, and they have a lot of calibration models that they have to maintain. And we do have a paper on this, and you can find that. I'll put a note also later on when I post the video, but here's a link to the paper at the bottom here. Now, I just want to talk a little bit about how you maintain models, normally calibration models. And when I say calibration models, I'm usually thinking, you know, type PLS models and stuff like that. But it really could be anything. It could be neural networks or support vector machines or Gaussian process models, whatever. It's all the same principle. But when you do have to maintain calibration models, there's a lot of classical things that you look into, and there's also, as some of you will be familiar with, there's a number of standards that tells you how to handle calibration models. Often that will be based on NIR, near infrared spectroscopy kind of models, or infrared models, but the principles are more or less the same. And you would typically, while you're using your model, you will assess in different ways whether the model continues to work as intended. And sometimes you will have control samples where you also measure the reference. So if you're trying to predict color, you're gonna measure a sample where you know what the color is going to be. Or you may measure samples and determine that suddenly samples that were normal are now seeming like outliers, things like that. So there are different ways that you can monitor, but you typically end up with some kind of statistics, like a Q statistics or Hotelling's t-squared, or it could be the bias in your predictions. And then you run that in some kind of control chart to make sure that things are going fine. And if not, then you have to do some kind of correction. Once you've done a correction, then you will also go in and verify that the correction actually did as you intended to. Now, all of this is fine and good. You also have to look into, once you have a problem, what is actually causing the problem. Is it the instrument that has changed? Is it the samples that are different, that come from a different population? Or is it the calibration model that needs to be dealt with? And depending on what you find, you may sometimes do with simple bias corrections. That is done quite often when you maintain models, or maybe slope bias. But generally, when you run into slope, at least when you run into a lot of slope corrections, you may actually have to recalibrate your model. This is also, what I'm saying here is just to give you an idea about the work needed for doing this, and different areas can have different traditions. But the main thing is that maintaining your calibration models is something that requires a lot of effort and actually a lot of resources. And typically, for example, in the good old days of process analytical technology, when that was introduced, that was typically left out of the business cases when companies were saying that they needed to implement this and that calibration model. They tended to forget that there's also some maintenance afterwards. But it is a substantial, and those who work in companies where you have hundreds of calibration models will know that it really is a substantial effort, and therefore there's also an interest in how can we lower the sort of the workload of maintaining calibration models, which is what I'm going to talk about here. Now, before I do, I want to mention, I don't know if you're familiar with Barry Wise. I work a lot with him, so he's a very nice guy, but apart from being a nice guy, he and Bob Roginski has also written several papers about calibration model maintenance, and those are really excellent. They have sort of formalized all the concepts that you need to take into account. And I mean, when you look at a chart like this one, it seems a little bit intimidating. But the thing is, if you want to maintain calibration models, you do have to look into and understand when things are deviating, what it is you have to correct. Is the model, is it the instrument, is it simple, is it complicated, must I recalibrate, etc. And I'm not going to talk about these things here, but the papers they have written are excellent, and I really recommend that you look into those. What I'm specifically going to talk about is the situation where you just have a large number of calibration models that you're maintaining, and I want to show you a way to lower the number of models that you have to maintain. And in this particular case, the data that we used in the publication I mentioned, and that I will link to and show you, that was from a dairy company where a certain factory was receiving products from other dairy companies. And each of these products from other dairy companies had their own model. So that would be 10 or 20 different calibration models. And each of them had to be maintained separately. Each of them had to have their control charts. And every now and then they had to be updated either with a slope intercept or with a recalibration. And that was the problem. So initially, the dairy company, instead of having all these different models, what they thought was, well, maybe we could actually combine them somehow. So instead of building individual models on each and every data set, they wanted to combine them. And what's the most obvious way to combine your calibration models? Well, what many people will try to do is that they will merge all of them into just one single data set. So now life is simple because we only have to maintain one particular calibration model. And for this particular calibration model, well, you will then get an error. I'm writing a root mean squared error, but it could be anything depending on what you're interested in, but something like that. So I hope that makes sense, that we now, if we have combined everything into one model, we have a total error. Now, originally, here we have 9 different data sets. Originally, we have 9 different PLS models, or whatever kind of model we have. So we would have one model here with an RMSE. We would have a model of calibration set 2, etc. And each of them would have an error estimate. Now I can combine all these error estimates into one number, so it's comparable to this. So I can compare how these 9 calibration models are doing as compared to one calibration model. I will have to correct for the number of samples, but that's sort of trivial. But I can always monitor, even though it's 9 different models, I can look at their quality in terms of one overall root mean squared error. Okay. Well, it turns out that quite often this is not a good idea to combine all your data into one model. Sometimes it is, but in many cases, this is not a good idea if you want to have nice predictions. So the alternative would be to use less, but how do we find out which calibration data sets we should merge? And we do that here in a very simple way. So what I'm going to do initially is that I'm going to take these two and I'm going to combine them into a single model. So I'm going to build one model here where I just get a total error. So I still have this one, this one, this one, this one, this one, and this one. So now I have 8 different models. Okay, maybe this was not the smartest one to combine 1 and 2. So I'm also going to try to combine 1 and 3 instead. And again, now I have 8 different error measures, and I can combine them into one number. And if that total error is better now, then it's smarter to merge 1 and 3 than 1 and 2. And basically what I'm going to do is that I'm going to keep on merging until I have tried all combinations of 8 clusters, of 8 models. And I'm going to pick the best one. And in this particular case, it turned out that merging calibration samples from 1 and 2 into 1 would give me the lowest total error. So now I have one model here. Before I had a model of calibration samples from situation 1 and situation 2, but now I just have one combined model. So now instead of 9 models, I now have 8 models. And I can continue now. I can move on and I can see if I can merge these 8 clusters into 7 clusters like this. And in this particular case, I found that merging samples from calibration situation 8 and 9 would give me the lowest total error. So if I only am allowed to have 7 different calibration models, then this would be the nicest way to cluster my models. And I keep doing this. So in this case, now I have one cluster which has data from 3 different situations, and I have these single ones, and I have a double one here. So now I have 6 clusters, and I continue all the way down to a model which has just all the samples in one cluster. And for each of these, I get a yellow error, a blue error, a red error, a green error, and I get this error. So for each and every number of clusters, I would get an error message, error measure. And I can therefore combine and compare and see what happens when I combine. So let me try that on the samples. These are IR spectra from dairy products, trying to predict, in this case, protein. We had different things we wanted to predict. Now, if I take samples from each and every factory, there's 10 different factories. If I take them individually, then I get an RMSE CV as noted here. So this is the combined error of all the 10 different factories, but it's based on 10 PLS models in this case. Okay, let's try and combine them. If we want to combine them, it turns out that dairy company 2 and 6 should be combined into one, and the other ones should be kept individually. And you see, there's hardly any change. We kind of get the same result. And it turns out that for protein, that's the situation basically all the way down to 2 or at least 3 clusters. So you see here that I can actually, instead of the current situation, where we're having to maintain 10 different models, I can cut that down to only having to maintain 3 different PLS models. One will be from just factory, dairy 1. One will be from just dairy 4. And the other one is really a combination of the remaining 8 ones. And this sort of also makes sense from what we know about the dairies, but that's another thing. But it's quite spectacular that you only need to maintain 3 different models, and you have exactly, well, maybe even slightly better predictions. If we want to go all the way down to 1, so put all the data into one big pile of samples and build one calibration model, you see that that actually will cost you quite a bit on the predictions. Note that this is not 0, so it may look a little worse than it really is, but you do kind of double the error by going all the way and put all the samples into one big pile. And this is actually what many people would do if it's kind of live in one of these extreme. Either you live with the complexity of maintaining 10 calibration models, or you say, okay, let's combine everything and now life is easy from a calibration maintenance point of view. But you can see how much it'll cost you in prediction error. Now, if you don't mind that, if this is still well within what you need your models to perform, then definitely you could go for that. But in general, you would say that that's probably not a good idea, that it's sort of bad to fuse everything into a global model, and that free models is maybe the right compromise. That's still a threefold sort of improvement in calibration maintenance and no price in prediction. Sometimes you would even improve your predictions. Now, in this particular case, we could actually also have done this from looking at the protein levels. And we did, and we achieved a similar performance. But the thing is, we have a way to test this here. We have a way to see, is that really the optimal, or should I go for one grouping, or should I go for 2 or 9 or whatever? So we can really get an idea about the cost of different choices. Now, we also try to predict other things like the fat content. And here you see, for example, there's no reason not to merge everything. We get an improvement and we only have to maintain one model. So rather than the situation as it is today, where people are merging into, not merging at all, but maintaining 10 different models, we can actually just always use everything into one model. That also has the advantage that, imagine that you are now making a new product or a new recipe, or getting samples from a new factory, as is the case here. Well, in this case, I would expect that the model would also work for new dairies. Whereas if I'm looking at the protein, I may actually be a little bit skeptical. I would have to figure out which grouping it would have to go into, which is another problem that we're not going to talk about here. But it shows here that for the fat, we can expect it to work on all similar kinds of dairies. Okay, let me just turn off Natalia. Thank you. So there's a question here: which RMSE is used for clustering the models? Well, in the function that we have for doing this, I'll show it later on, it's using the RMSECV. So the RMSEP is just used for monitoring. You can input a test set, but it's not going to be used. It's using cross-validation for selecting how to group. You could imagine building a tool that would only use the test set, but we chose to use the cross-validation. Okay, so that was fat. We actually also have dry matter, and it's sort of similar to the protein. It's a really bad idea to merge everything into one model, but it seems like there's hardly any price of going down to 2 clusters, or maybe 3 clusters, depending a little bit on how much you trust your error measures. But this is really this is the gist of it, that you can actually get a visualization where you can easily see how much does it cost me to make different choices. So we can automatically fuse the models, and we can choose to select, you know, the balance between how many models do we want and how well do we need it to perform. Sometimes we can even improve the models. We didn't see much improvement here on these data sets because they were fairly large, and so each individual model was already fairly well sort of posed. But sometimes if you have shaky small data sets, then clustering them could actually help. Now there's a question: why not use a single local model? Well, whoops, let me just go back here. If you use a single local model, that means that, for example, when you look at this case, we have 10 different localities. That would mean that you have to maintain 10 different calibration models, and that's a substantial amount of work. Both lab technicians and chemists and process operators would be very happy if there was only 2 control charge, but also only 5 times fewer sort of situations where you have to recalibrate, because depending on how you recalibrate, it's a significant workload. So that's why we don't want to just have individual models if we can avoid it. That's the thing is, if you look at this plot here, there's really no argument for having 10 different models. You could imagine some arguments maybe, but looking at the plot here, there's no argument for not having 2 models. Why would you build individual models? If I'm building linear regression, why would I build 1 regression line here and 1 regression line here if they work well together? There's not really any argument for doing that. So also statistically, it is kind of evident that when you get results like this, basically that's an argument in itself. But from our perspective, it was also because it means less work. And there's a clarification here that it would be a locally weighted regression model. That's another alternative. That's perfectly fine. Anything that is written here can be done with locally weighted regression models as well. So you could also build locally weighted regression models, having 10 different ones, or combine them. You could test locally weighted regression models here as well. It doesn't have to be PLS models. So the principle would be the same with a local model. You can still test, is it fine to make locally weighted regression models where I keep everything together or not? So you could test that. But locally weighted models are as a way to avoid handling this problem, but it comes with the cost of being more difficult to maintain. So how do you evaluate when the model is not sort of still useful? How do you evaluate when you have to recalibrate your locally weighted regression model? Not that it cannot be done, but it's a more difficult and challenging task, and I'm guessing that in some regulated environments it wouldn't be as easy. Not sure about that, but I think that might be a problem. So okay, and then there's a question if there's also a way to overcome instrument variations. So for example, if I have instruments that are different, sometimes when we have, you know, we bought the same 2 versions of the same instruments, but it turns out that if I build the model on one and predict with the other, we don't really get nice predictions. And sometimes you can use what is called calibration transfer, which is maybe not the most fortunate name, but to change the 2 measurements to look like 1 measurement. And definitely this could be used for that as well. You know, it could be used. Let's say you have 10 different instruments, just to make life simple. So I could make individual models on the 10 instruments, or I could check here which of my instruments could actually be merged. So if I end up with something like this, I would say, wow, there's something fishy going on with instrument number 1 and 3. So maybe we have to look into this and figure out if they are actually working okay. So yes, it could be used as an alternative to calibration transfer. And again, depends on the application, whether that would make sense or not. I'm not saying it's always going to be, well, it's not going to be better per se than calibration transfer, but it's an alternative, or even an alternative to understand where you have to do calibration transfer. And there's a question of whether we can also use this for qualitative models. In principle, yes, but the way it's built now, it's built on prediction. So you could use it for, let's say you do PCA models. You could look at how well you predict your data matrix. This is what you do when you do cross-validation of, for example, PCA models. But it's a little less clear that this would be, I mean, that's what you want. Do I really want to predict my whole matrix in PCA? But to the extent that you think you do, or you are happy with doing it, it could in principle, but the way it's implemented now, that is not technically possible. And which brings me to that I would like to show you how we implemented this. So let me just end the slideshow like this. Here we are. And let's take MATLAB. Come on. Here we are. Okay, so we have a function called Clusterfun. And what I'm going to do is that I'm going to load some data. This is the data. It's a spectral data set. And let me just look into it and show you what it looks like. Here we are. So it's a spectral data set of, let me see, how many samples did we have? We have about 700 samples measured at 160 wavelengths. I'm using MATLAB here, and I'm using PLS Toolbox. I'll get back to that. So some of these samples come from one plant, one factory, another factory, etc. And in this particular case, I have IR data, and I want to predict the protein content. I'm not going to go too much into the actual application here, but I want to show you how it's run in MATLAB. So it's a command line function. That means you have to run it through scripts like this. So I'll just go through it very shortly. It's as I said, it's very much based on PLS Toolbox. We use PLS Toolbox a lot here, both for teaching and for developing. And sometimes we even get some of the stuff that we do in the toolbox. So it's also sometimes available through PLS Toolbox. I'm not going to talk more about that since that's not really the issue here. But the way we build it, we are using that as an engine, because that means we don't have to worry about pre-processing, about cross-validation. All these things are already handled. So I start by defining some options, and let me just show you what they look like. These are the standard options for what I'm going to run. So now it could be that, let me show you here the data. For this particular data set, just need to get the data back in. There we are. Yeah. So for this particular data set, we have our class in the first one, but there are actually, I could have many classes. I could have different operators. I could have different products, different raw material, whatever. So I can actually specify which of them we're going to use. And this is related, this is not relevant here. I can also specify which Y reference in case I have many Ys, and also the maximum number of PLS components. Then I define pre-processing for X and for Y, and I'm going to show you how to do that. And I can also have a look at and modify the cross-validation options. So I can define that this is leave one out, blah, blah, blah. I can define different types of cross-validation options. In this particular case, I'm going to use Venetian blinds and 10 segments. If you're not aware what that is, there's help on the internet on explaining that. It's not important here, but it is important when you decide how you want to run your cross-validation. It depends on your data. And also there's options for PLS if I want to change something, if I want to use a robust version or whatever. I'm not going to do that. So this is just my options that I'm going to use to make sure that we're running it the way I want to. And then I can define pre-processing. So why the protein is going to be mean-centered. And for the spectral data, I'm going to do SNV, so kind of a scatter correction, and followed by mean centering. So that's basically it. If I wanted to, I could even say, hey, I would like to try different types of pre-processing. So I could define, instead of just one called SX, I could also define another one that's called SX2 and one that's called SX3. The point here is just that I can define all kinds of pre-processing. And what is going to happen is that each and every time you're building a model, it's checking all combinations. So it's checking which of these three is the best one for each and every little PLS model it's doing. So in every decision, it's just taking the better one. We're not going to do that here because of time anyway. But if I did, I would just test all the combinations. This is the function. We can open it up and have a look. There's a little bit of help text on how to use it. And there's a lot of outputs. I can give my calibration data. I could also give test data, and then the options that I have defined. Okay, so let me run that now. So in this particular case, I have 6 different classes. So first, it's going to start out by building a local model on the 6 different classes. And then it's going to start merging. So from 6, I want to go to 5. So first, I'm going to check, as the first dot here, I'm checking cluster that sample 1 or calibration set 1 is merged with 2. Calibration set 1 is merged with 3. Calibration set 1 is merged with 4, 5, 6. And then calibration set 2 is merged with 3, is merged with 4, 5, 6. Calibration set 3, etc. Kind of boring. But anyway, so it's testing each and every one exhaustively. And if you have many clusters, so many factories or whatever it is you're trying to cluster, then that can take quite a while. But then, of course, as we go down, it's going to get faster and faster and faster. So now I have found the best of these 6 classes to merge into one. So now I only have 5 clusters to test, of which I should merge. And you can see that is way faster than when we had 6 clusters. And now, of course, we're down to 4. And that's going to be even faster. So that's sort of the nice thing. Once we're done with the first ones, it's going to be fairly fast. So let's take a look now at the results. And of course, they end up in the wrong screen. Here we are. So I didn't have, oh, don't do that. I didn't have a test set. So I'm just going to get the root mean squared error of cross-validation. And you can see that when I do individual models, I get an error of, well, you can see it here, 0.057, so something like that. If I merge class 2 and 6, I actually get a lower error, but not really by much. If I then also merge 5 and 7, I even get a lower one, but really not by much. And if I put class 4 into that, I still get this low error. But now, if I try to go further down than 3, you see that the error will increase sort of significantly. So it's kind of clear here that 3 classes would be the optimal here, rather than 6. Now, there's a question whether the number of components are optimized to minimum RMSECV, and indeed that is the case. So we're using cross-validation to select the number of components. And that's why it can be a good idea to keep this one fairly conservative. It depends on what you like, but certain types of data will happily improve insignificantly up to 20, 30 components, and also in situations where I wouldn't want to use that. That's a matter of taste or science, but I prefer to be a little bit conservative on that. Now, I don't just get this total error, I also get, let's see if I can find it, the error of the individual clusters. So this is my error initially. I have class 2 to 6. So actually this red bar is class number 3. So class number 3 is behaving, let's say, strangely. And then 2 gets merged into 6. So this is still class 3. So you can see that class 3 seems to be a little bit weird from all the other ones, and that might be something that we should look into. So we may actually want to understand why that is the case. That's not sort of the issue here, but you can see that we get some more detailed information to understand where these numbers come from. So this number, the error that I have when I have 5 clusters, comes from these 5 RMSE CVs weighted by the number of samples. And if I had a test set, I would also get a bias estimate, because then we also can see the bias of each and every model cluster. Okay, I hope you sort of get the idea. And if you want, you can get the function for doing this. I'm afraid we're trying to transition our website, so we're not going to put it on the web, but I can easily send it to you. So just send me a mail if you're interested in playing around with this, or interested in seeing the paper. You can also find it on the internet if you want. And if there's any questions, please let me know. And regardless, I'm going to stop